So here's what we have left. So we got projectile motion, which is going to take us like 3 days to get through, kind of Monday, Tuesday, Wednesday. Usually I do that in the last 9 weeks, but because that all got screwed up, I'm going to have to do it now. And then we'll have like a short, just like a simple quiz over that, not a big deal. And then we will start then circular motion, and then that'll lead into gravity, and then from there we'll do momentum, and then we'll do energy, and then we'll do thermodynamics, and then we're done. So those are the big things that we have left. Okay, so the cool thing about projectile motion is that there's no new equations to learn. It's just kind of repackaging the equations that we already have. So with projectile motion, there's two broad types of problems. One is what I call a lemming problem, and the other one is ground to ground. Okay? So anybody know what lemmings are famous for?
Falling blindly.
Yeah, and then jumping off of a cliff. Okay, so the legend of lemmings is these in England. There are these little things that look like rats, okay, gophers, something like that. And they all run off to the edge of this cliff and they all jump into the ocean. Okay, so on a lemming problem, you can have something shot out like this. Okay, and then on a ground to ground, the simple version is that's going to be like a golf club shot that goes something like this. So today, we're only going to focus on the lemming problems, and then tomorrow we'll deal with the ground-to-ground problems, and we'll do live on that on Wednesday, and then we'll call it good. So here's what's going to be common to both of them. Now, what's going to be different is that up to this point, we've either dealt with like the horizontal motion, okay, where like a book is being pushed along like this, or the book is dropped, and we look at the acceleration of that, okay? Those are the two options that we've had. So what we're going to do with lemming problems is that we're going to combine both of them into the same problem. So we're going to have horizontal motion, and then we're going to have vertical motion. So here's the mantra of both of these problems. And it's kind of like, if you've ever seen the ads on television for Vegas, like what happens in Vegas stays in Vegas, okay? It's kind of the same idea of what's going to happen here. What happens in the X stays in the X. What happens in the Y stays in the Y. And those calculations are separate, but then we combine them at the end. Okay? So here's your kind of mantra. What happens in the X stays in the X. What happens in the Y stays in the Y. So the key assumption that we're going to make on both of these is that the horizontal velocity is going to remain constant. Okay? Now, here's the deal. This is where everything kind of gets tied up together. So, I'm going to take this and I'm going to throw this to Shivani. You ready?
Oh, yeah.
Okay? You ready? Okay. So, when I throw that, I gave that ball a certain amount of horizontal velocity. And I'm going to assume that whatever horizontal velocity I gave it at the beginning is the same horizontal velocity it's going to have when she catches it. Now, when you look at this from a forces perspective, if the horizontal velocity is constant, okay, so if you were to look at a vertical velocity Vx versus time graph, okay, that's just going to be a horizontal line. We're going to assume that that's going to remain constant. So which of Newton's laws says, oh, I'm going to give it a certain amount of horizontal velocity and that's going to remain constant. It's not going to change. Which law is that?
Inertia.
Yeah, law of inertia, Newton's first law. So what we're going to assume is that when I gave that golf ball a certain amount of horizontal velocity, certain Vx, we're going to assume that there are no forces acting horizontally. Okay? So there is no gravity mafia, there is no horizontal mafia, nothing happening horizontally. Okay? So when you throw that back,
Okay.
I got it. Nice, nice, good throw. Okay, so we're going to assume that whatever horizontal velocity is given, okay, is the same horizontal velocity because there is no force, so there is no acceleration. Now, what's the one equation that you can use when you have horizontal velocity? What's the one? You can only use it in one situation.
Oh, when the velocity is constant.
When the velocity is constant. What's the one equation you can use when you have constant velocity?
V equals D over T.
Huh?
V equals D over T.
Yeah. Or distance equals velocity times time. Right? Okay? We've done that, you know. Not a big deal. You can only use that when you have constant velocity. Now, what we're going to do is we're going to write this a little bit fancy. And we're going to call it range equals Vx time. So this R is going to be range, which is going to be how far the ball travels horizontally. So in this situation, the range would be the distance from me to Shivani, however far I threw it. Okay? It's going to be, if it's on a golf ball, it's going to be how far you hit the golf ball. Okay? So it's going to be however far that ball travels horizontally. This is your Vx. Notice that is not your vertical velocity, has nothing to do with this. Yeah, when I throw it to Shivani, that ball is going to begin to fall vertically, but that's what's happening in the Y. There's nothing happening horizontally, and then you have time. Okay? So all this is on a velocity time graph. That's just this is just this Vx times time. That range is just the area underneath that velocity time graph. Okay? That's all it is. It's just Vx times time. That's it. Okay? Now, here's the deal. Vertically, we are going to have an acceleration. Now, you play soccer, right? Both of you play soccer, right? If you've played soccer in Kansas and there's a strong south wind, you know this statement really isn't true if there's a wind. You know when you kick it into like a strong wind, that ball is going to get knocked down. Or if you kick it with the wind, that ball is going to go a lot further. Okay? So we're going to assume that there is no horizontal acceleration because then you get into drag coefficients and wind and everything else like that. Okay? So that's why we're just going to assume that our Vx is going to stay constant. Vertically, there is going to be a force because vertically you do have the gravity mafia. So we are going to get an acceleration vertically, but we're not going to get an acceleration horizontally. So on both of these, the only force acting on it is gravity, right? And we know what that acceleration is going to cause because that's going to be mg. So on both of those, that vertical acceleration is going to be negative 9.8 meters per second squared. So whether I throw it horizontally or if I throw it on a path like this, the only force acting on it is gravity, and you know what that acceleration is going to be. Okay? All right. Now, pretend that none of that exists for now. We'll get back to it. For now, I want you to pretend that none of that is there. We're going to go back to the acceleration unit. And I'm going to hold a ball up to a height of 2 meters, and I'm going to drop it. Okay? Just drop it. Boom. Just like this. So pretend that you're getting ready for the acceleration test. Okay? Pretend that you're getting ready for that. And this ball is going to fall 2 meters, and my initial vertical velocity is going to be 0. I want to find out two things. I want to figure out how long it's in the air, and I want to figure out how fast it's going right at that point of impact. Okay? Right at that point of impact. So, Miss Pfeiffer, I know how far it falls, and I know the acceleration, so how can I figure out how long it's going to take to fall?
V squared equals B naught squared.
No, I'll do that. Hold on to that thought. I'm going to use that one. I'm going to use that equation to find the velocity.
V equals B naught plus AT.
Close. How about we try distance equals 1/2 AT squared plus V naught time. Okay? How about we try that one? Now, here's the deal. I'm going to drop it. So what's my initial velocity?
0.
0. Okay, so that's going to be 0. Do I know how far it falls? Yeah. I know my acceleration, the only thing I don't know is time. So time is going to equal the square root of 2d over a. So technically, Matt, get a calculator out and divide it by negative 9.80 meters per second squared. So take 4 and divide it by 9.8 and then take the square root of that. You're going to get 0.6 something.
Yeah, 0.639.
Okay? So I'm going to hold it up here, right? I'm going to let go of it. 1 missa, okay? So 1 missa is about equivalent to 0.639 seconds. Okay? So that's how long it's going to be in the air. So our velocity time graph would start like this. And we're here. And that line's going to slope down like this. It's going to have a slope of negative 9.8 meters per second squared. It's going to be in the air for 0.639 seconds. Okay? Now, here's what I want to know. Why did I not have to tell you that this was a top flight golf ball?
Because you're just dropping it?
Yeah.
Doesn't matter.
Doesn't matter. Okay? Doesn't matter. Could you plug into this equation the type of golf ball that it is? No. Okay? Can't put it into that equation if you try. You can't plug in the number of dimples. It's not there. Okay? The fact that it's a white golf ball as opposed to a yellow golf ball. Okay? Not a factor. Did I even have to give you the mass of the golf ball? No. So here's what's going to be important. And as we get into more and more complex equations, you need to think through about what is the factor and what is not a factor. Okay? So here's the deal. What are the only two factors that determine how long that ball is in the air?
Distance.
Distance and
Gravity.
the acceleration due to gravity, right? Okay? That's it. Now, there's actually a third thing that plays into this, and that's the idea that my initial velocity was equal to 0. Okay? But assuming that your initial velocity is 0, because I dropped it, okay? My initial velocity is 0. So the only thing that determines time is how far it falls and the acceleration due to gravity. The mass of the ball, the fact that it's top flight, the fact that it has 72 dimples, whatever it is, none of that makes any difference. Okay? Now, let's talk about how fast it's going to be going when it hits the ground, right? So Elise correctly said, oh, I can use v squared equals v naught squared plus 2ad, right? Now, what's my initial velocity going to be?
0.
0. Okay? So that's going to go away. So v is going to equal the square root of 2ad. So Matt, take 2 times negative 9.8 meters per second squared. Technically times a negative 2 meters. And then take the square root of all of that. And you should get 6 point something
6.26.
meters per second. Okay? So that's how fast it's going at the point of impact. Now again, what is the only thing that determines how fast that ball is going when it hits the ground?
Distance.
Distance and
Acceleration.
acceleration due to gravity. That's it. Okay? That is it. Nothing else matters. Mass doesn't matter. Nothing else. It's only how far it falls and the acceleration due to gravity. Okay? That's it. Nothing else. Okay? Now, what I'm going to do is I'm going to take this handy dandy little device and I'm going to put it up there on the shelf. And what it's going to do is going to take one of these marbles and I release it and that plunger is going to come out. And we'll talk about energy later. I'm storing potential energy in the spring. And when I do that, I do work. And Mother Nature hates potential energy because when I let go of it, it immediately turns into kinetic energy. So I'm storing energy. I'm exerting a force over a distance. I've stored energy. So I'm going to do this, I release it, this thing's going to get shot out horizontally. Okay, so this is like me tossing this ball to Shivani. Okay? Now, on the back side, this one has a hole in it. Okay? Like here. And when I shoot it, then that ball is going to begin to fall. So here's the idea. This one's going to get shot out like this. So it's going to go, okay? This one's going to fall straight down. So here's what I want you to think through, okay? Here's what I want you to think through. So we have one ball that's going to fall straight down. We have another ball that's going to come out like this, okay? So we have one that's shot, and we have one that's dropped. So there's three possibilities in terms of which one is going to land first, okay? So option A, the ball that's dropped is going to land first because it's just going to fall straight down. Option B, the one that shot out is going to hit first because I'm going to give it some initial velocity and then it's going to fall faster. Okay? Option C is going to be at the same time. Okay? Those are the three options. Dropped, shot, same time. Okay? So, what do you think is going to happen? Miss Pfeiffer.
What was the question? Sorry.
Which ball is going to hit first? The one that falls straight down, the one that gets shot, or are they both going to hit at the same time?
The one that's dropped.
Why?
Because, I don't know, I just think it will.
Okay, it's just a gut feeling,
Yeah.
and sometimes that's valid. Matt, as you sit there and tie your tie,
Yeah.
tying a tie.
Theoretically, I think they would come in at the same time.
Why?
Because they both have the same negative vertical acceleration.
Yeah. Okay. Are they both going to fall the same vertical distance?
Yes.
Yeah. Okay. Kara, what do you think?
I think you want to drop, go first because, hit first because it's just going down.
Yeah.
It's getting shots going horizontal too.
So it has more distance to fall, so it should take
Well,
longer.
it's not more distance to fall, but it'll take, the one that's shot will go horizontal and the one that's dropped will just go
Okay.
vertical.
All right. Shivani?
The same time.
Same time?
The same
Why?
acceleration.
So we've got same vertical acceleration, okay? So we have two that say the drop ball, and two that say they're going to hit at the same time. Okay, so I'm going to spin the camera around, and let me get this set up over here.
It's like it's a shot and we're all wrong.
Huh?
I said it's like it's B and we're all wrong.
No.
Looks like it's the drop ball.
Yep, it's a drop. Where did that drop? Okay, so we spin. Okay, so here's the setup. This one's going to fall straight down. This one's going to get shot out. Okay? So you ready? 3, 2, 1.
That sounded like the same time.
They did hit at the same time. Okay?
Period.
They did hit at the same time.
It's still going.
I know, I've lost my marbles. Which happens all the time.
Only one of them, though.
Huh?
Only one of them.
Yeah,
though.
that is
I
true.
lost all of mine at this point.
Oh, you're young. You still got a long way to go.
Can't do this more time, though.
Oh, yeah, you got me there.
Okay. So here's what happened. is that they both landed at the same time. Because if you go back and look at time, which was 2d over g, they both fell the exact same distance of 2 meters, okay? So the fact that there was a horizontal velocity is not a factor in that equation, okay? It's not there. You cannot plug Vx into that equation if you try. Just like you cannot plug the mass of the golf ball into that equation if you tried, okay? Can't do it. Can't do it. So assuming that they're both shot horizontally, one's dropped, the other one is shot with just Vx, they're both going to be in the air the exact same amount of time. Because what would happen is that they're both going to begin to accelerate vertically. So they're both going to have that same vertical velocity. The only thing difference is that this one's going to have a Vx, and that Vx is going to remain constant. Okay? So now, let's say we want to figure out what that Vx is. Well, that ball landed about 1.5 meters from where it was launched. Okay? So we know that range equals Vx time. Okay? Range equals Vx time. So let's say that that traveled 1.5 meters. And the time it took was, what was the time, Matt? 0.639
Yeah.
seconds. Okay? So, Shivani, you're fine, child. Chill out. My God. I know you lost your marbles, but I think you have enough left to solve this equation. I have faith in you, okay? So, I know how far it went,
Yeah,
okay? And I know how long it was in the air.
yeah,
So I want to find Vx.
yeah.
So what am I going to do?
R over T.
There you go. See, was that so tough?
No.
See? It's okay. Stay with me, okay? So you got range over time equals Vx. So I'm going to take 1.5 meters and divide that by 0.639 seconds.
2.35.
So call it 2.4 meters per second. Okay?
Right, my bad.
Which isn't all that fast. I mean, I'm old and I can run faster than that. Okay? I can probably walk faster than that.
It would just be 2.3 because I ran it up to the 5.
Okay. All right, 2.3. Now I know I should be faster than that. Okay, so I got 2.3 meters per second. So here's vertically or horizontally on your Vx versus time graph. That's going to be exactly at 2.3 meters per second. So your horizontal velocity versus time graph is just going to be a horizontal line. And that's going to be 0.639 seconds. And the area underneath that graph is going to be 1.5 meters because that's how far it went. Okay? Got that? No worries. So now, vertically, it is going to accelerate. So what we know at this point is that when this ball lands, okay, so just at that point of impact, okay, just at that point of impact, we just figured out that it had a horizontal velocity of 2.3 meters per second. So there's our Vx. And what was that Vy, Matt? 6.26?
Yeah.
Okay? So here's the deal. When this ball lands, and this is what's different, up to this point, we've talked about an object having like a vertical velocity, okay? Kangaroo jumps up in the air, you shoot a cannonball, whatever, okay? We only talked about horizontal velocity. Or we've talked about horizontal velocity. Oh, how fast is the car going, okay? Whatever that is. But now we have two different components. So now we have a horizontal velocity, and then we have a vertical velocity. So what we can do, and this is where you get into the terminology is so important. So you've got a Vx of 2.3 meters per second, and then you have a Vy of 6.26 meters per second. So what I want to do is I want to calculate the speed. So I want to know how, like, imagine that you had, when this ball was landing, imagine that you had a tiny little, like, radar gun that the cops use to track how fast you're going. So imagine that you had a tiny little radar gun, and you want to figure out how fast that ball is going right at that point of impact. Okay? Right at that point of impact. So here's what I want you to think through. If you know two sides of this triangle, right? Miss Pfeiffer, how can I figure out the result?
I don't know.
You studied geometry.
Yeah,
Ever heard of Pythagoras?
yeah. I didn't know if you could do that. Okay.
Yeah, it's at a right angle.
Okay. So yeah, it's
A squared plus B squared.
equals C squared.
There you go. Okay? So Matt, let's do a little A squared plus B squared equals C squared.
6.69.
What'd you get?
6.7.
6.7 meters per second. Okay? So that 6.7 meters per second is the resultant of a horizontal velocity and a vertical velocity. So that's how fast the ball is actually going. But it has two components to it. It has a horizontal component to its velocity, and it has a vertical component to its velocity. Okay? Now, on the lab, I'm also going to want you to find this angle. Okay? And don't worry about this being, measured around from 0 degrees. I just want this angle. So on the lab, I'm going to expect you to find this angle. So, Kara, what trig function, knowing the opposite and the adjacent, could I use to find that angle?
Tangent.
Beautiful. Okay? So Matt, let's do a little inverse tangent action of 6.26 divided by 2.3.
Okay, yep, 69.
69 degrees. Okay? So on the lab, this is one of the things I want you to be able to do, because what you guys do, you guys roll a marble down a ramp, and you're going to have a Vx and you're going to have a Vy, and you want to find that angle. Okay? Now, let's play the what if game. Okay? And there's two ways that you can think this through. So here are the two big equations with lemming problems. There's three equations. Time equals the square root of 2d over g. V equals the square root of 2ad. And r equals vx time. Okay? Now, remember, this comes from distance equals 1/2 at squared plus v naught time. And again, what happens in the x stays in the x, and what happens in the y stays in the y. We're assuming that our initial velocity is 0. We solve for time. This comes from that equation, that v squared equals v naught squared plus 2ad. Okay? And again, we assume that the initial vertical velocity is 0, and we end up with this, and that's just distance equals velocity times time. So every problem that you're going to do with lemming problems is going to involve those three equations. Okay? So on the lab, on the assignment, every problem is going to be some variation on that theme. Okay? That's it, nothing else. So here's what I want to look at. Let's say instead of falling from 2 meters, I'm going to double that. Okay? And I'm going to make it fall from a height of 4 meters. Okay? So instead of falling from 2 meters, I want to make that fall from 4 meters. So, Shivani, right now I don't want a number, but I just want to kind of quantitatively think through this. If it falls, instead of 2 meters, it's going to fall for 4 meters. Okay? What's that going to do to the amount of time that it's in the air? Will it increase, decrease, or stay the same?
Increase.
Increase, right? Gravity has more time for it to act. So it's going to be in the air longer. It has more room to fall. Okay? So it's going to be in the air longer. Kara, what's that going to do to my velocity when it lands then?
When it increase?
It's going to be going faster, right? It's going to be in the air longer. Gravity is going to have more time to act on it. It's going to be going faster. Okay? Vertically, it's going to be going faster. Matt, I want to make it fall 4 meters. Okay? What's that going to do to my Vx?
No,
Absolutely nothing. Why?
it's Vegas.
Vegas. What happens in the X stays in the X. What happens in the Y stays in the Y. So when that thing was launched, it had a certain horizontal velocity. No matter how long it's in the air, it doesn't matter. Okay? It doesn't matter. It's all going to have the same horizontal velocity, no matter how long it's in the air, because we're assuming that there's no horizontal acceleration, because we're assuming that there's no horizontal forces. Now, what I want to be able to do is quantify this, okay? I want to be able to say exactly how much does that change. Now, there's 2 ways that you can do this. One option is smash mouth physics, okay? And you can go, okay, I'm just going to take 2 times, instead of 2 meters, I'm going to take it times 4 meters divided by g. So Matt, take 8 divided by 9.8 and the square root of that.
Oh, I had that. I deleted it.
Ooh, why did you do that?
I don't know. Must be Monday. 0.90.
0.90 seconds. So one option is that you do smash mouth physics. Okay, you just plug in the new numbers. Now, here's the more elegant approach. Okay, and I don't care which one that you choose. I don't care which one that you choose. You just have to pick one. Okay? So the other option is that you go, okay, well this was 2d over g, right? That's how you're going to calculate how long it's in the air. So then you look at the new condition, which we're going to call t prime, okay? And get used to this idea of t prime, or v prime, or momentum prime, okay? The prime just indicates that you're going to be looking at a new condition, okay? That's all it's going to mean. So this would be 2 times 2d over g, okay? So because this is what we would do. If we want to double how far it's going to fall, we're going to take d and we're going to multiply it by 2. If we tripled it, it would be 3d. If we quadrupled it, it would be 4d. If it was half as much, it would be 1/2 d, okay? So it's just going to be however you're going to change that system, right? Now, y'all have done algebra, right? So can I do this? Can I write that as the square root of 2 times 2d over g? Is this legal? Can I just pull out that 2 and write it like this? Kara?
You make it sound like it's not. I don't know. I haven't been in a math class in a year.
Okay? Okay, so who's the math nerd that's willing to take the fall on this one?
Matthew.
Matt?
What? Like you want to
Is
take it
this
out?
legal what I did?
Yes.
Yeah, it's very legal.
You
Okay?
made it sound like it wasn't, and I was
No, I
thinking-
did not. I would never try to trick you, Kara. Come
I think
on.
you have.
Huh?
Think
I've
you-
what?
Why
Tried
are you
to trick
looking
you?
at me?
Well, I
I
think
didn't
you
say
said.
anything.
Okay. Shivani, I'd never try and trick you guys. Okay, maybe just a
Okay.
little. Okay, yeah, this is perfectly legal. Now, here's what I want you to do, Matt, just for the fun of it.
Okay.
Okay. Our original time was 0.639 seconds, right?
Sure.
So I want you to take the square root of 2, and I want you to multiply that by 0.639 seconds.
That's not what I want to do.
And let me know what you get.
0.90.
You get the exact same answer. Okay? So you could either go with an elegant approach and go, oh, it's underneath the radical. So if I double it, I'm going to increase it by the square root of 2. Or you can make up numbers and actually put in the values. Okay? I don't care. It doesn't make me any difference. If you triple it, guess what? It's going to increase by the square root of 3. If you quadruple it, if you go up by a factor of 4, then what's going to happen? Otherwise known as 2. So if you want to double the time, you have to actually increase your height by a factor of 4. Okay? Now, the same thing is going to happen with your velocity, because that's also underneath the radical, right? So if I increase the distance and doubling it, guess what? My velocity is also going to increase by the square root of 2. My vertical velocity is going to increase by the square root of 2. Okay? If you triple it, it would increase by the square root of 3. Okay? Makes sense. Okay. So what you have to look at is what is going to be a factor and what is not going to be a factor. Okay? And then you look at that and go, okay, well, what's going to happen through all this? Now again, think this through. We said that range equals Vx time. True? That's what we said. Now, this is where we tie together some different things. If I double the height to 4 meters, what's that going to do to my Vx? Absolutely nothing, right? My Vx is not going to change. That's going to stay the exact same. Okay? That's going to stay the exact same. But we just said I'm going to increase my time by the square root of 2. So if I take the exact same Vx and multiply that by the square root of 2, what's going to happen to my range? It's going to increase by also the square root of 2. Okay? Now, let's play this what-if game. What if instead of shooting it out at 2.3 meters per second, I pull that plunger back farther and I launch it at 4.6 meters per second. Okay, so now I'm going to double my horizontal velocity. Okay, so now I'm going to make it shoot out twice as fast, horizontally. Okay? What's that going to do to the amount of time that it's in the air? Matt?
No.
Nothing. Vx is not a factor. So if I make that marble go twice as fast when I shoot it out, it's not going to change how long it's in the air. Will it go further? Yeah. But it's still going to take the same amount of time to fall because Vx is not a factor. It's also going to land with the exact same vertical velocity because, again, Vx is not a factor there. Will it double my range? Yeah, it's going to go twice as far. So the mantra is, what happens in the x stays in the x. What happens in the y stays in the y. The only time you combine both of those is when you're trying to find the speeded impact. Okay? Got it? Good? Grand? Okay. Let me hand out the lab. Okay, so here's what you're going to do. You're going to take a ramp like this, and you're going to clamp it onto the table. Make sure that there's this little tab on the bottom. Make sure that that's like off the edge of the table so that the ramp isn't tilted up like this. So make sure that that's exactly clamped down like this. Then you're going to take a little marble like this. You're going to hold it up there at the top. You're going to let it go. It's going to roll down. You stored potential energy, which Mother Nature doesn't like. You let it roll down. Boom. It's going to come out like this. It's going to have horizontal velocity only and no initial vertical velocity. Gravity is going to kick in and it's going to begin to fall. So, in terms of data, here's the only data that you're going to need. It's going to come out like this and it's going to land. So what you want to do is roll it the first time and get an idea of where it's going to land. Then you want to put down a piece of plain paper and then you want to put a piece of carbon paper over the top. So what carbon paper does is kind of cool. So and make sure that you put the diamond side up. So you've got this, just take a small piece of tape and just kind of secure this a little bit. And then when that marble hits, what it does is that it transfers an image from the carbon paper onto this. So this is if you do emails or you get like CC, carbon copy, that comes from carbon paper. So how back in the, when dinosaurs ruled the earth, when you would type, okay, number one, you didn't have printers. With the old style printer, you would hit like letter A and it would strike the paper, okay? B, boom, okay? So if you want, and this is before copiers were prevalent at all. So if I wanted to type a letter and I wanted Matt to have a copy of it, so what I would do is I would have my original piece of paper. Then I'd put a piece of carbon paper, and then I'd put another piece of paper behind that. So that way when I press the letter, I want to type Matt. So I'd type capital M, boom. The speed ball or the letter, whatever it was, would come up and it would hit the paper. And that would type the letter M on the front. Then that physical pressure would transfer that to the paper that was behind it, and then that's how I would get the second copy. So when you see CC on an email, that stands from carbon copy, and that's how you used to make copies. And if you had like 3 people that wanted them, you'd have 3 pieces of paper. Now, by the time it got to like that third one, it would be kind of faint because you lost a lot of that energy in that transfer. But that's where CC comes from on your email. This is the old way of typing and how you would get a carbon copy. So, here's the data that you need. You're going to measure this range, okay? You're going to measure how far it's going to go. And then you're going to measure that vertical distance and how far it's going to fall, okay? That's the only data that you need. You're going to calculate the time, okay? Do not ask me for a stopwatch. You're not going to time it. You're going to calculate the time, and then you're going to get range, you're going to get Vx, Vy, all of this stuff. Now, what I want, when you get down here to V resultant, and notice I want to see calculations, okay? Do not, the only thing that's not going to require a calculation is the measurement of range, time, and height, okay? For your time, I want to see that calculation. Vx, your initial vertical velocity, there's nothing to do with that. Vy, V resultant. So what I'm looking for on V resultant, at that point you're going to know Vx, you're going to know Vy, and this is what I want. I want the hypotenuse of this triangle, because this is going to be a right angle. And then I also want this angle right here, okay? Don't give me the one that goes all the way around like this. I want this angle, and that's usually around 70 to 80 degrees, okay? So, collecting the data in this lab is going to be pretty simple. You're just going to have it roll out, clamp it, get an idea of where it's going to land, measure to the top of the ramp, down to the floor, okay, so you know how far it falls, and then you're going to have to measure. And this gets a little bit tricky, so you got to like transfer that point down to the floor, and then from that point on the floor, measure out to that point where it landed, okay? So the only bits of data that you're going to measure is the height of the table, how far it falls, and that horizontal distance. Now, when you get to the back side, when you get to, you got a car driving off a cliff, it's 112 kilometers per hour. What are you going to do with the kilometers per hour? Change it into meters per second. Okay? So you're going to figure out how long it's in the air, how far, your range, horizontal velocity, vertical velocity, the speed. Okay, that's going to be that resultant of Vx and Vy. Now, when you get to that next set of questions, I'm going to say if the horizontal velocity was doubled, how would each of the following change? And I tell you, and I don't care how you do this, you could either tell me, oh, it's going to double, it's going to triple, it's going to increase by the square root of pi, whatever it is, okay? Or if it doesn't change at all, just put it doesn't change. Or, just looking out seeing sunglasses on upside down. So, or you can actually do smash mouth physics and calculate the value, okay? I don't care which one that you do, okay? I don't care. I do not care. Either calculate it, do smash mouth physics, or tell me how it's going to change. But just don't say, oh, it increases or decreases. Okay, if it changes, I want that numeric value. Okay? All right, so here's the three big equations that you're going to need for this lab and that assignment. Time equals square root of 2d over g. D equals the square root of 2ad. H equals vx time. Okay, I am done. You're on your own, and let's go do science.